Hello Game Makers, this is Game Maker Rob, and in today's episode we have the start of a pathfinding system where we can click in a different part of the map and we get the cells or the nodes that we can travel to from that particular node with a range of 6 tiles. So let's get started. Okay, so we want to be in the step event of our Battlescape object, and I need to make a quick apology. I should really have stuck with my original code from when I first coded XCOM. Back then I was using objects for nodes, and this time round I decided to use structs without realizing that you have a problem with recursion whenever you're storing structs within arrays of different structs. And if you store one struct in another struct, it doesn't like it very much. It doesn't work. It creates kind of problems. So I've just changed it to objects instead. There actually isn't a lot of work involved, believe it or not. All we need is we want a new object called obj node. There's no code, no sprite, it's just an empty object like this. That's all we need. And then in obj Battlescape, in the step event, in our create node structs region, we want line 211. Whenever we make a new Battlescape, we want to get rid of any existing nodes first of all. That's what this is for. And then we have this region here, create a node for every cell. And then this code here was making a struct for every cell, but we're going to replace it with this. So instead of making a struct, we're going to make an instance of obj node and store it inside our all nodes array. And then with that node, that object that we just created, we're going to have these two variables as before, nodes edge all and nodes walk. But we also want to know the grid X and grid Y for that particular node, because it doesn't know itself. And we want to have a distance variable and a parent variable, and all 4 of these are going to be very useful for pathfinding. Grid X and grid Y should be pretty self-explanatory. Distance is going to change depending on the start node. So distance is basically how far away am I from the start node, and it depends on the parent of this node. So basically a parent of a node is when we are calculating a path for a unit to travel, we want to generally know the shortest path to get from point A to point B, and then each node has several different adjacent nodes that it connects to. Sometimes you might only have one, but usually there's at least 2 or more. And to know what we're going to do in one of our scripts is we're going to calculate the closest node from between the start point and the current node, and that's going to be the parent. It might not make much sense right now, but it will do as we go along. Let me just minimize this region. And we have this new array called nodes within range. This is what's going to display our nodes that are within range. So if you remember at the start of the video, I was showing you, I was clicking on different cells and other cells were highlighting. Those are the nodes or cells that are stored within this array. And then in the ready section, we have a new region called Pathfinding. This is again just for testing purposes. Whenever we click the left mouse button, we're going to get the start node, which is whatever node the mouse cursor is over, and it's going to be based on the current level cursor X and cursor Y. And then we're going to say, okay, so how far away will the movement be? And we're going to say we're going to give it a range of 6 for now. And then we're going to use a new script called SCR display action nodes. We're going to pass it our start node and range. And this script is going to fill this array with every node that can be reached within this range. So once we've got this down, let us dive into this script. Okay, so let us make a new script called SCR display action nodes. I'm going to go into the script now, jump to the top. So like I said, we're going to be passing the start node and the range, and it's just going to fill our array here with all the nodes that are within the range. This basically is my version of A* pathfinding. I'm not going to go into a full depth explanation of how A* pathfinding works. I am going to try and explain it, you know, just so you have a grasp of it. But as long as you know that when we run the game and say for example we click here in the corner, then all of these nodes that are within, basically all of these nodes are within 6 movement points of this corner here. And right now diagonals are being counted as being the same as adjacents, which we may or may not change as we progress. If I click here, you can see all of these nodes are within range. You know, wherever we do it, we're going to get like a similar result. You can see all these nodes are within range, and all we're doing basically is we click on a cell. This cell says, okay, which are my adjacent nodes, which are the 8 around it, and it says, are we within range of 6? Yes, we are. Then add it to nodes within range, and then all of these nodes get their adjacent nodes added, and the same check applies. And we have, as you can see, we have a queue, a priority queue called open, and an array called closed. And whenever we check a node to see if its neighbors are within range, it gets added to closed. And if a node is not within range, it gets added to closed and won't be added to open. So we're not going to check its neighbors, and that's the basics of how it works. And because we're using, you know, a limited amount of range, then we don't need to search the whole every single node, because it's only going to get as far as 6 plus 1, because all those plus 1s are not going to be within range. So anyway, let's go on with this. So we have open, which are the nodes that we want to check, and we need a priority queue because we want to be able to check the nodes that are closer to the start point first. This usually means that we'll have the correct parents, because we want parents to be the shortest path between the start point and the end point. Closed, again, is the nodes that we don't want to check, or that we have already checked, basically. A nodes within range. I'm just remaking it here. It doesn't have to be called this, it can be called anything. We're going to be returning it at the end, and it's just going to store the IDs of all the nodes that are within range of the start node. The first thing we want to do is, even though at the start of the game these two values are going to be 0 and no 1, after the first click that's no longer going to be true, so we want to reset them for every node. I've just thought of a better way. If we didn't clear this first, we could just search the array and clear it from that. That would be a bit faster, but it's not really a big deal on our performance, so I'm not going to make that change right now. So again, we're just at the very start of the script, and we want to add our very first node to open, which is our start node. And the priority we want to add it to is the start node's distance, which is every node's priority is going to be its distance. We could just type 0 for this, and it's going to be the same because the distance between the start node and itself is 0. But this hopefully just kind of sets the tone for how we're going to be doing it for the rest of the nodes. Current is going to be the current node that we are checking the neighbors of, and we're going to be grabbing it from open. And remember, only the nodes that are within range of the start node get added to open. So while the size of our priority queue is greater than 0, right now it has a size of 1, but we're going to be adding more to it. We're going to say current equals ds priority delete min, which gets us the closest node to our start node. The first thing we're going to do is add it to our closed array so that we no longer check it again, because I've done that before now. I've forgotten to add things to the closed, and then it just means you're rechecking the same nodes over and over and over again, and actually you just end up with a never-ending loop. So that's why we're doing it first of all, to make sure I don't forget it. Okay, so we have all of the nodes that we can walk to from our current node stored in neighbors, and we're going to be going through that whole array where there can be a maximum of 8 neighbors, and we're going to get each node in turn, and we're going to store it in add node, and we're going to check to see, okay, is this add node already enclosed? If it is, then that means we've either already checked it. Oh, sorry, it means we have checked it, and we've either already added it to open, or it's outside of our range and we can pretty much ignore it because it's going to be useless for our pathfinding. So if add node is not inside closed, that means it hasn't been checked yet, and it may well be within range. Let's change that, and maybe. So we're going to be using parent as a variable to help us determine a path, which we're not going to do today, but it helps if you understand what this is for. And basically a node's parent should be the node which is closest to it and the start node, because sometimes, for example, you'll come across a node which has a distance of 4, and then another node next to it only has a distance of 2, and then to get the shortest path, that node with a distance of 2 should be this node's parent, because then this distance will not be 4, it will be the current node's distance, which is 2 plus 1. So using parents is how we get the shortest path, and it's how we calculate a path as well. I'll explain that in more detail, and also have some code for it in the next episode. So anyway, what we want to do next is we want to calculate this adjacent node's distance, which we're just going to say for now is the current node's distance plus 1. So when we have the start node, first of all, that's going to have a distance of 0, and then all of the nodes around it are going to have a distance of 0 plus 1, and it's going to increase like that until eventually we'll be getting distances of 7 or greater, which means this is no longer going to be true. But as long as this is true, as long as the distance for our adjacent node is 6 or less, we're going to be adding that adjacent node to our open queue, and the priority that we're going to be adding it is going to be the node's distance. We're also going to make sure that we add this adjacent node to our nodes within range array, because we can move to it. So players might not always want to move their full movement range, they might only want to move 1 tile. That's why we're going to add it there. And then regardless of whether the node is within range or not, we're going to add it to our closed array like that. And then if the node has already been added to the closed array, we're just going to check to see if current is a better parent. Basically, if the current's distance +1 is less than the adjacent node's distance, then we set the parent of the adjacent node to the current and set the adjacent node's distance to the current node's distance +1. And then once we've checked all of our nodes, there's going to be no nodes left inside open, so just destroy it. And then we're going to return nodes within range. You don't need this show debug message. I was having some performance problems, so I want to make sure how fast this script ran. That's all that message was for. And that's the end of the script. So if we go back to the step event of OBJ Battlescape, you shouldn't have any yellow or red markers here anymore. All of this should look the same as I have it. So then we want to go into the draw event now, so we can actually see our work take place. So in the draw event, we're going to draw the west walls again. So line 26, comment this out and just replace it with what we had before, which is checking if there is actually a sprite to draw for the floor, walls or decoration. And then we had the code for testing nodes walk. I've actually commented it out, and we're going to have a new for loop that takes care of testing nodes walk and our new array, nodes within range. So we have two loops, sorry. Basically, running this check inside this double for loop was giving me bad performance issues. It was dropping to like 10 FPS, sometimes 2. So I just did a for loop here, and all it's going to do is go through nodes within range, get the nodes grid X and grid Y, convert it into a draw X and draw Y, and then draw that node in black with an alpha of 0.5. And then nodes walk, we're going to be doing the same thing, except we're going to draw it in olive 0.5, just so we can see the two together. One last thing that I did as well is in the draw GUI event, line 27, I'm grabbing the node that's within the current level and the cursor coordinates, and I'm showing the parent of that node and the distance, although this isn't really that useful because it's either going to show us no one or an ID, and we're not displaying the ID of the node as well, so maybe we should do that first. Let's change that here as well. If we're going to have debugging stuff, it might as well be useful. Some of these things I don't realize until I'm making a video on it, and it just kind of pops out like, oh yeah, that could be better. There we go. So that is all of the changes. Let's run the game now. And then you can see wherever we move the mouse over in the middle bottom left, the node value changes. And if I click somewhere, then we have all of these highlighted nodes, and then the parent value changes. So you can see this is our start node ending 478, and then the parent of 479 is 478, and the parent of 480 is 479, and that's how we're going to calculate a path, because we're going to, when the player clicks on, say for example he clicks here, then we're going to run a script which starts from here until he gets all the way to the start node, and it's just going to make an array of the parents. So the parent of this node is 100533, which is this one, and then the parent of 100533 is 482, which is this one, and then 482's parent is 532. Oh, I'm sorry, so 532's parent is 482, which is this one. 482's parent is 481, which is this one, and then 481's parent is 480, which is this one, and then so on and so on until we get to the start node. That's how we generate a path using the data we've done, and hopefully you can see why we bothered setting up all of the nodes in the way that we did in the first place. It's so that we can do pathfinding like this, so we can, you know, add nodes to an array to say, okay, these nodes are within range, and then we can generate a path from wherever we click on these nodes to wherever we want to get to. If I move my mouse over some nodes further away, you can see their parent is still no one, and the distance is 0 because they never ever got checked. As soon as we got to like here, like all of these nodes on the outside, they did get checked, but because their distance was 7 or greater, they never got added to the open queue, so we never checked them, and we never had to bother about all of the outside nodes. And that's a good thing, because we would have been checking probably 20, 30, 40 times as many nodes or more. You know, if we were doing that, you don't want to check every single node in your game just for pathfinding. So I'm going to stop waffling now. Thank you for watching, guys. I will catch you next time. Bye for now.